The early life microbiome may quietly sculpt the blueprint of our lifelong relationship with food, hunger, and even how we experience reward. In the first 1,000 days of life, from the womb through infancy and toddlerhood, the gut undergoes a massive colonization process that doesn't merely support digestion or immunity. Increasing evidence suggests that it also plays a key role in programming the neurocircuitry of eating behavior, shaping how the brain interprets hunger, satiety, and food pleasure long into adulthood. This colonization is not random. At birth, babies acquire microbes from their mother through vaginal delivery or skin contact, and then rapidly accumulate a succession of microbial populations shaped by breastfeeding, formula, antibiotics, environment, and early food exposures. During this sensitive window, the gut-brain axis is particularly malleable. The vagus nerve is still wiring its reflexes, hormonal patterns are forming, and neuropod cells, those remarkable gut sensory cells that speak directly to the brain, are calibrating their thresholds for detecting sugars, fats, and microbial metabolites. One of the most striking aspects of this period is that the microbiome appears to co-develop with the nervous system, acting not only as a passive resident, but as a kind of neural sculptor. Animal studies show that germ-free mice, those raised without any gut bacteria, have abnormal stress responses, underdeveloped vagus nerve signaling, and disrupted dopamine and serotonin pathways. When these mice are colonized with a normal microbiome early in life, some of these deficits are corrected. But if colonization happens too late, the changes become permanent. This suggests that microbial signals are essential for the normal maturation of brain regions involved in food motivation, emotional regulation, and interoception, our sense of internal physiological state. More specifically, certain early microbes may train the brain to associate particular nutrients with pleasure, safety, or discomfort. For example, Bifidobacterium species, dominant in breastfed infants, help metabolize human milk oligosaccharides into short-chain fatty acids like acetate and butyrate. These compounds don't just feed the gut lining, they modulate satiety hormones like GLP-1 and PYY, influence dopamine signaling, and strengthen gut-brain communication. Infants exposed to more diverse and balanced microbial environments may develop a more finely tuned neurobiotic sense. Their gut can accurately detect when it's full, when something is off, and which foods are rewarding for the right reasons, not just calorie density. Conversely, disruptions to early microbial development, such as from C-section delivery, early life antibiotic use, or formula feeding, have been associated with higher risks of obesity, picky eating, sugar-seeking behavior, and even anxiety or ADHD later in life. These associations are not simply behavioral, they are increasingly understood as reflections of altered microbial training of gut-brain pathways. For instance, a less diverse microbiome may blunt the activity of neuropod cells that detect sugar and send reward signals to the brain, causing the child to seek more intense stimulation through food. Or dysbiotic gut communities may fail to generate sufficient SCFAs, weakening satiety signaling and promoting early overeating patterns. What's more, early microbiome patterns appear to leave a lasting metabolic imprint. Several studies have found that the types of bacteria dominant in infancy can predict body mass index and insulin sensitivity in adolescence, even when controlling for diet and physical activity. This suggests that the microbiome may lock in certain metabolic tendencies toward leanness or weight gain, toward satiety or persistent hunger, by shaping hormonal rhythms and neural responsiveness to food cues. Crucially, this early microbial programming also affects how individuals emotionally relate to eating. Children with altered gut microbiota profiles may show higher stress reactivity and lower emotional self-regulation, making them more susceptible to using food for comfort or control. The gut's microbial signals help set the tone for how the brain interprets internal sensations. Is this discomfort hunger, boredom, or anxiety? The clearer and more accurate these internal cues are, the easier it becomes to develop a balanced and intuitive eating style. Yet there is hope and plasticity. The microbiome remains modifiable, even after early life disruptions. Introducing prebiotic fibers, fermented foods, diverse whole plant-based meals, and targeted probiotics during childhood and even adulthood can help remodel gut communities and restore more accurate gut-brain signaling. Breastfeeding, when possible, remains one of the most powerful ways to support initial microbial and neurobiotic development, followed by gradual exposure to varied textures, tastes, and fiber-rich solids during weaning. In summary, early life microbiome development is not just about immune health or digestion. It is a foundational architect of our eating instincts, wiring the gut and brain together in a shared sensory language that defines how we feel hunger, how we know we're full, and what kinds of foods we seek out. This neurobiotic programming doesn't disappear as we age. It guides our preferences, behaviors, and vulnerabilities for years, if not decades. Recognizing the importance of this early microbial shaping opens up powerful opportunities, not just for preventing disease, but for cultivating lifelong metabolic resilience, emotional balance, and a more trusting, accurate relationship with food.